In this lecture, I'm going to introduce you to an important concept, and that's the concept of flux. We're going to start by talking about electric flux, and then we're going to do magnetic flux a little later. So to begin with, let me remind you some of the basics of electric fields. Okay, so around a point charge, the electric field lines either all point away or all point in. They point away from a positive charge and they point in to a negative charge. And remember, the electric field direction is telling you the direction of the electric force if you were to put a positive charge in the field. So if I put a positive charge over here in this field, it's going to be pushed away by this positive charge. If I put one over here, it's going to be attracted by this negative charge. So the arrow tells us the direction of the electric force, which is simpler than what we were just doing with the magnetic field. In order to get the direction of the magnetic force, from the magnetic field, we had to use a right-hand rule. This one is much simpler. It's just the same or the opposite direction of the field direction, depending on whether you have a positive or a negative charge that you've put into the field. Another shape of electric field we've seen is the electric field between two plates, like in a parallel plate capacitor. And here the electric field is all pointing in the same direction. All the electric field lines are parallel. Unlike this, in this situation, the electric field lines are not parallel. But they can be parallel, for example, between two charged plates. And the electric field is uniform, approximately uniform. But that's an approximation that we've been using frequently. The electric field is uniform between the two plates, meaning it has the same magnitude everywhere. So now let's talk about the concept of flux. The symbol for flux is capital Phi. We're talking about electric flux. Later we're going to talk about magnetic flux. To differentiate between the two, we can put a subscript E on here to remind us that we're talking about electric flux. I'll probably just write it as Phi for now. And the idea of flux is it is a measure of how much the field lines are penetrating a surface. Okay, so I'm going to quantify all that in just a minute. But one thing that is immediately apparent is that if I have more lines going through a surface, then we should have a larger flux. So again, the flux is a measure of the flow, if you like, of the electric field, in this case, through the surface. Now you can do the flux for any vector field. A vector field is, we've seen several examples of a vector field. Electric and magnetic fields are vector fields because it's a vector everywhere. At every point in space there is a vector. And you can do the flux of any vector field. It could be the flux of the velocity vector field of the flow of water, for example. And I think that the flow concept is a useful one. Backing up to these pictures for just a second, I want to point out that notice what's going on with the field lines close to this charge. They are more closely packed. There's less distance between adjacent lines here. And if I were to draw more lines, because there's actually an infinite number of these lines, if I were to draw more, you'd see the density would clearly be pretty high. The density of field lines would be high around close to the charge. Far away from the charge, the density is lower. We also know from what we've done with electric field before that the strength of the electric field is higher closer to the charge and weaker farther away from the charge. So that tells us a relationship that we can use when we're examining electric field lines. And that relationship is that the electric field strength, and by strength I mean magnitude, is proportional to the density of electric field lines. So the more closely packed the electric field lines are, the higher the magnitude of the electric field. Going back to this one, I already mentioned that this electric field is uniform, meaning it has the same magnitude everywhere. And if you look at the density of the electric field lines, it's also uniform. It's the same everywhere. So this relation holds in that case too. If we have evenly spaced electric field lines everywhere, then that's a uniform electric field. So back to this picture, if I want to know how much an electric field is flowing through this surface, clearly the more field lines that I have that are piercing the surface, the more electric field I have going through the surface. And more field lines piercing the surface means that those field lines are more densely packed. So by that reasoning, the electric flux should be proportional to the density of the field lines, which is proportional to the strength of the electric field. So our first conclusion about the electric flux is that it's going to be proportional to the magnitude of the electric field. So stronger field means more field lines, which means more flux, more lines penetrating a surface. Okay, another thing that we can conclude about the electric flux is if I had let's say this surface has an area A. If I make this surface bigger, so it has a bigger area, then you would expect more electric field lines would be penetrating the surface. It seems pretty straightforward. And if I make it smaller, then there's going to be fewer field lines piercing the surface. So based on that, I can also conclude that the electric flux is going to be proportional to the area of the surface. By the way, this surface could be physical, like a sheet, or it could be imaginary, meaning that it's defined only mathematically. All of these arguments will still hold, whether this is an actual physical surface or just a mathematical surface. Okay, and then the last piece we need to talk about to understand electric flux is the direction of the electric field. So I've drawn two examples here. Here the electric field is perpendicular to the surface, and so the electric field hits the surface flush, straight on. Over here, we have the electric field is parallel to the surface, and I think you can see that, especially if this is a mathematical surface that has no thickness, then none of these electric field lines are penetrating the surface. They're just skimming along the surface, but none of them are actually traveling from one side of the surface to the other. And then my third example is the same as my first one, except that I've reversed the electric field direction. So if we're talking about how much electric field is going through this surface, it would make sense to have these have opposite signs. So this would be maybe positive flux, and this would be negative flux. Okay, so here we expect the flux to be 0. Here, this is the maximum amount of flux that we can get. So let's call this one +1, and let's call this one -1. And so we need to include the direction of the electric field, and it needs to take on values between +1 and -1. And so that right away suggests that we might be talking about a sine or a cosine. Now, to make this more concrete, we need to talk about an angle. So we need to define some things so that we can talk about an angle. So if I have a surface, then I'm going to define the unit normal. Normal means perpendicular. So this unit vector is perpendicular to the surface. And it's a unit vector, so it has length 1. Okay, and let's say we have some electric field lines passing through this surface. Then if I put the unit normal right at the point where the electric field line pierces the surface there, then I can define this angle between them. I'm going to call that angle theta. So returning to this, what is theta in this case? Well, the unit normal points out of the surface, perpendicular to the surface. And all of these electric field lines are perpendicular to the surface, so theta in this case is 0. Here, the unit normal points outwards, perpendicular to the surface, and these are parallel to the surface, so there's a 90-degree angle between E and the unit normal in this picture. And here, I have the unit normal pointing out, but the electric field lines are going in. So these are anti-parallel, right? So in this case, theta is 180 degrees. Okay, so can you think of a sine or a cosine, a sinusoidal function that is 1 at 0 and 0 at 90 and minus 1 at 180? Yes, that is cosine. So the last piece to our electric flux is that it should be proportional to the cosine of theta, where theta is this angle between the electric field direction and the unit normal direction. All right, so putting all that together, we have that the electric flux is proportional to 3 different quantities. So I'm going to define it then to be the product of those 3 quantities. So that is the magnitude of E, the surface area, A, cosine theta. Turning for a moment to this picture, we can use the property of dot products to write that the dot product between E and n hat is equal to, and then this is just a property of the dot product, or a definition if you like, it's the magnitude of E times the magnitude of n hat times the cosine of the angle between them. But the magnitude of n hat, this is a unit vector, so this is just 1. So this is equal to E cosine theta. And if we look down here, we see we have an E magnitude cosine theta. So I'm going to substitute E dot n for that down here. And I get E dot n times A. Another thing I want to point out here is that E cosine theta is the component of this electric field vector that is parallel to n hat. So you could call this in words, this product E cosine theta is the component of the E field that's perpendicular to the surface. So the electric flux is proportional to the component of the E field that's perpendicular to the surface. That's E dot n, as well as the area A of the surface. Okay, now in principle, we shouldn't expect the electric field to always be uniform, which means that this magnitude E can vary across our surface. Unless it's a uniform electric field, we should expect that the electric field is going to be different at different places in space. Therefore, it may not always have the same magnitude when it's piercing the surface. So with that reasoning, what we're going to do is we're going to let A be some small area, delta A. This small area being small enough such that the electric field is uniform over that small area. Okay, and then if we do that, now we need to find the total flux through a surface. We need to sum up all of the delta A's. So we get a formula that looks like this, where we are summing over the entire surface this quantity. And by the time we do the entire surface, all of those delta A's are going to add up to the total surface area of A. So this is going to give us the total flux through the surface. Okay, one last step. We are going to make delta A infinitesimally small. So now in that case, our claim that delta A is small enough so that E is uniform over delta A is absolutely true, because we're making delta A infinitesimally small. So the electric field must be uniform over that area. So when we have a sum where we're making this term infinitesimally small. So delta A goes to dA. And as we know from the definition of the integral, if I do that, the sum becomes an integral. All right, so this is the last step. I can write my definition of the electric flux as the integral of E dot n hat dA. This used to be delta A. We made it infinitesimally small. And this is over the whole surface. And this notation, put a circle here, just means over the entire surface, we're going to take this integral. All right, so that is our electric flux.